The photoelectric cutoff voltage is the minimum voltage that will stop all of the emitted electrons. This occurs when the kinetic energy of the electrons is equal to the potential energy of the electric field. The potential energy of a particle with charge Q in an electric field with potential V is given by P equals QV. In this case, the charge of an electron is minus 1.6 times 10 to the minus 19 C and the photoelectric cutoff voltage is 1.5 volts. The potential energy of an electron at the photoelectric cutoff voltage is then P equals minus 1.6 times 10 to the minus 19 C. 1.5 volts equals minus 2.4 times 10 to the minus 19 J. The maximum kinetic energy of the emitted electrons is then equal to the potential energy of an electron at the photoelectric cutoff voltage, which is 2.4 times 10 to the minus 19 J. A. The energy and momentum of each photon in the light beam can be calculated using the following equations. Energy, E, equals hc, lambda. Momentum, P, equals h, lambda. Where h is Planck's constant, 6.63 times 10 to the minus 34 Js. C is the speed of light, 3.00 times 10 to the 8 meters per second. Lambda is the wavelength of the light, 632.8 times 10 to the minus 9 meters. Plugging in the values, we get E equals 6.63 times 10 to the minus 34 Js, 3.00 times 10 to the 8 meters per second, 632.8 times 10 to the minus 9 meters, equals 1.99 times 10 to the minus 19 Jp equals 6.63 times 10 to the minus 34 Js, 632.8 times 10 to the minus 9 meters, equals 1.05 times 10 to the minus 25 kilograms meter per second. B. The number of photons per second, on average, that arrive at a target can be calculated using the following equation. Number of photons, N, equals P, E. Where P is the power of the light beam, 9.42 times 10 to the power of minus 3 W. E is the energy of each photon, 1.99 times 10 to the power of minus 19 J. Plugging in the values, we get N equals 9.42 times 10 to the power of minus 3 W, 1.99 times 10 to the power of minus 19 J, photon, equals 4.74 times 10 to the power of 15 photons, S. C. The speed of a hydrogen atom that has the same momentum as a photon can be calculated using the following equation, V equals per meter. Where P is the momentum of the photon, 1.05 times 10 to the minus 25 kilograms meter per second. M is the mass of a hydrogen atom, 1.67 times 10 to the minus 27 kilograms. Plugging in the values, we get V equals 1.05 times 10 to the minus 25 kilograms meter per second, 1.67 times 10 to the minus 27 kilograms, equals 628 meters per second. To determine the number of photons incident on the Earth per second per square meter, consider the following steps. 1. Calculate the photon energy. The energy of a single photon can be calculated using the equation E equals hc, lambda, where E is the energy in joules, J, H is Planck's constant, 6.63 times 10 to the power of minus 34 Js, C is the speed of light, 3 times 10 to the 8 meters per second, and lambda is the wavelength in meters, 550 times 10 to the minus 9 meters. E equals 6.63 times 10 to the power of minus 34 Js, 3 times 10 to the 8 meters per second, 550 times 10 to the minus 9 meters, equals 3.60 times 10 to the minus 19 J2, relate photon energy to power. The power reaching the Earth's surface is 1.388 times 10 to the power of 3 W per square meter. Recall that power is the energy transferred per unit time, represented as P equals E, T, where P is power in watts, W, E is energy in joules, J, and T is time in seconds, S. 1.388 times 10 to the power of 3 W per square meter equals 3.60 times 10 to the power of minus 19 J, T. 3. Calculate the number of photons. To find the number of photons per second per square meter, divide the power by the energy per photon, N equals 1.388 times 10 to the power of 3 W per square meter, 3.60 times 10 to the power of minus 19 J, photon, equals 3.84 times 10 to the power of 21 photons, square meter per second. Therefore, approximately 3.84 times 10 to the power of 21 photons are incident on the Earth's surface per second per square meter. The photoelectric cutoff voltage is the minimum voltage